All right, in this next section, 10.5, we will take a look at two new convergence tests, the ratio and root tests, and then we'll discuss some basic general strategies for how we might want to employ these tests that we've learned over the past few sections. So first, we'll talk about the ratio test. The ratio test is a way of examining the ratio between successive terms of the series. So as we look towards the very far down along the sum of that series, we look at the terms. As we look further and further along in that sum, what does the ratio of two adjacent or successive terms, in particular the nth term and the n plus first term, if we look at that ratio, what's the limit of that ratio? Now, if the ratio between two successive terms is less than 1, then that means the terms are getting smaller. They're getting smaller. If the ratio is greater than 1, that means the terms are getting larger. So it's not surprising that if the terms are getting larger, we would conclude divergence, and if the terms are getting smaller, that we would conclude convergence. Another thing here about the ratio test that's important to know, because we're examining the absolute value of this ratio, that means the conclusions that we draw about convergence would not just be convergence, but actually even stronger than that, it would be absolute convergence. If the ratio is 1, then the test is inconclusive. It may converge, it may diverge. So we don't need to go over the proof of this, but the basic idea is we are looking at what is the limit of the ratio of two successive terms, and if we get this ratio, the limit of this ratio to be some number that's less than 1, then if this ratio, the answer to the limit, rho, is less than 1, then that means there is some number, not just one number, but many. There's infinitely many numbers. There is, so let me rephrase this possibly. Let's say, so if rho is less than 1, then we can choose an r such that r is between rho and 1. We're free to do that. We're free to do that. For instance, if the ratio is 3/4, and that's less than 1, then I can definitely find a number between 3/4 and 1. For instance, I could pick 4/5. All right, so that's always true. No matter how close this rho is to 1, as long as it's strictly less than 1, I can always find a number between rho and 1. For instance, I could take the average of these two numbers, and that's guaranteed to live between. So it's always possible. So, since that's always possible, I can then compare, I can then essentially compare this series with a geometric series. And since this r, this value we chose, is less than 1, I know that this will converge. And then through the comparison test, this will ultimately lead us to conclude that the series itself converges by comparison. So the basic idea is the ratio test is a very convenient way of doing a comparison with a geometric series. There's some additional details that I'm sweeping under the rug there, which you can read in the proof if you'd like. But let's get started on this. So for the ratio test, determine whether the following series converges. So this series here, we immediately want to write down what our sequence term is. So the sequence is a sub n factorial over 100 to the n. And we can write down what the next term of that sequence is, the n plus first term. So this would be n plus 1 factorial 100 to the n plus 1. And for the ratio test, you'll always find it very convenient to rewrite your factorials like this and split apart those powers. The reason being is we want to eventually, since we're going to divide these two terms, we eventually want to cancel things. So we want things written in an equivalent way so that we can cancel them out. So now, for the ratio test, rho is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So we're going to take this a sub n plus 1 term, so this would be n plus 1 times n factorial over 100 to the n times 100. And then we're going to divide by this expression here, but we can just flip and multiply. So this would be 100 to the n over n factorial. Now the n factorials and the 100 raised to the n's, they will cancel out. And what's left over here is just the n plus 1 term and the 100. Now because n is 1 to infinity, and we're taking the limit as n goes to infinity, they're all positive, so these absolute value bars don't really do anything, so we can drop them. And we can see that when we take this limit, we're going to get infinity, which is definitely greater than 1. So this means rho is greater than 1, which implies that the series diverges by the ratio test. Example 2. Determine whether the following series converges: n factorial over n to the n. All right, so same thing. A sub n is n factorial over n to the n. And a sub n plus 1 is n plus 1 factorial all over n plus 1 to the n plus 1. I always like to rewrite this now, so I will do that with n plus 1 times n factorial all over n plus 1 to the n times n plus 1. Then, for the ratio test, we examine the limit of the absolute value of a sub n plus 1 all over a sub n. So a sub n plus 1, you can write that in. And then we'll divide by a sub n, so since this is a fraction, we'll just reciprocate and multiply. All right, so we'll have n to the n and an n factorial. Cancel what's in common. There's always going to be some stuff in common that we can get rid of. So what are we going to have here? The n plus 1s will cancel out. There we go. So again, as similar to the previous example, and this will be the case many times, all the terms within the absolute value bars are positive, so the absolute value bars don't do anything, so we are free to drop them at any point. So what's left over here is n to the n and n plus 1 to the n. So this is really n plus 1, oops, I meant to say n over n plus 1 raised to the n. Okay. So this limit right here, if we go ahead and actually take the limit as n goes to infinity, we would get the indeterminate form 1 to the infinity. Now some of you might think, well, isn't this just 1? Because 1 raised to any power is 1. And it is true that 1 raised to anything is going to be 1. But the issue here, the subtlety, and truthfully the more interesting thing going on, is that this number isn't actually infinity. it's taking on different values of n increasing towards infinity. Similarly here, this fraction is not equal to 1. It's actually always a number less than 1, but of course, as n goes to infinity, this ratio here does approach 1. So what's interesting here is this number is getting larger towards infinity. This ratio here is approaching 1, but neither this ratio nor this exponent are actually ever the values 1 or infinity. So what's interesting here is the fact that depending on the detailed nature of what this ratio is and what this exponent is, in the limit they may equal out to something that's different than 1 or different than infinity. It could be some number, something else. So to do this problem rigorously, what you would have to do is first define a function x over x plus 1 to the x, and notice that this x, it is a continuous variable. This n is a discrete variable. So if we were to plot this, if we were to look at the graph of this function, sort of like the discrete analog of it, it would just be a series of dots. It wouldn't actually be a curve. And since it's a series of dots and it's not actually a curve, we can't take a derivative here, because ultimately what we would like to do is use L'Hopital's rule on this. So it is a subtlety, and a lot of people probably won't take the time to actually think about this and pass to a continuous function. But really, you should actually first just need to recognize that we can define a continuous analog to this discrete function, and then the limit of this continuous analog is going to be exactly the same as the limit of this discrete analog. And then we can use L'Hopital's rule on this function when we take the limit, because it's continuous, and therefore it has an approximate derivative everywhere. So we can essentially look at this look at this continuous analog and take the limit as x goes to infinity of this expression here. Now, the way we would ultimately do this, well, I'm not going to go through all the steps because it takes a while and it's a Calc 1 limit, albeit a difficult Calc 1 limit. It is a Calc 1 limit. What you would do is, since e and natural log are inverse functions, it doesn't matter what I put in this box here, that those two functions, e and ln, they undo one another's actions. So they sort of cancel each other out. So I'm free to do e raised to the natural log of, and then I can put my expression in here, like that. Now the reason why we want to do that is because it would allow us to take this x all the way out in front, and then we'd have x times the natural log of just this fraction, because this exponent is now gone. And in this case, we can examine the limit of this and use L'Hopital's rule on that. So, skipping all of that work for now, what we'll do is just say what the answer is. All right, so with doing L'Hopital's rule and a bit of work, this would ... give us 1 over e. So this approach is 1 over e, and this is definitely less than 1, which implies the series converges. Remember, ratio test doesn't tell us just convergence, it tells us that it converges absolutely. So something a little bit more strong than regular old convergence. Last thing to mention here, that the ratio test is extremely useful when our series term, the sequence a sub n, involves factorials. But it will always fail if the series terms only involve powers of n, because the ratio will always be 1.